Hi guys, welcome to your next lesson. As ever, pause now if you want to write down your do now questions. They should be in your workbook, so if you want to just follow along and put the answers in. But pause it now and give it an attempt, that would be awesome. The questions are, number 1, what are the products of photosynthesis? What are the products of photosynthesis? So these are the things that are produced after photosynthesis. What chemical reaction that we talked about last week, and what are the products that are produced from that chemical reaction. Why do chemical reactions have to be balanced? Why do chemical reactions have to be balanced? And think about the law that we discussed. And number 3, what is the chemical symbol for carbon dioxide? What is the chemical symbol for carbon dioxide? Okay, have an attempt there and we'll do the answers together in a second. Okay, the answers to do now questions. What are the products of photosynthesis? So photosynthesis is that reaction that allows plants to create energy from sunlight, water and carbon dioxide. So we talked about it the other day, animals like humans cannot generate their own energy. They can't create energy from sunlight, but plants can. And we then eat animals or the plants directly to access that energy. So it's an amazing reaction. And glucose is a sugar, and it also produces oxygen. So plants breathe out oxygen, as it were, as a waste product. So they don't need the oxygen, but we do. So there's a nice kind of circular relationship that we'll talk about later on between plants and animals. Why do chemical reactions have to be balanced? Well, we talked about the law of conservation of mass. The law of conservation of mass states that energy cannot be created or destroyed, it just changes form. So that's why we looked at the equations last week when we had the reactants and the products. They have to balance on each side. And what is the chemical symbol for carbon dioxide? The chemical symbol for carbon dioxide is CO2. Okay, carbon dioxide is CO2. Okay, so I talked about Lavoisier, who came up with the law of conservation of mass, and I think it sometimes is lost on us how much information, how many people have looked at these things so that we know what we know now. And one of the really important things, I think, is to realise that we didn't know all the answers. We didn't know until fairly recently a lot about chemistry. And there's been so many people who have dedicated their lives to figuring out more on this subject. So today what we're going to look at is a history of the atom and how theories and models changed over time. The reason we're doing that is, one, it's interesting and it's relevant to the topic that we're looking at. But when I have you guys next year in year 11, there's a whole module called Theories and Laws. We talk about the law of conservation of mass next year again in more detail. And we talk about how theories change over time. And it's important to realise that a theory changes as new evidence is presented. And that doesn't mean that old theories were stupid, not at all. But it means that the theory has to change if new evidence suggests something else is going on. And it's quite nice to look at that example when we talk about the atom, because the theory of how the atom looks and what we have now has taken lots of very, very clever people, lots of time, and they've came up with multiple different theories and models and versions over the years. And we're going to look at a few of those now. So when we look at an atom, we usually draw it with the protons and neutrons in the middle of the nucleus and the electrons whizzing around outside. And you might just assume that we've known that for a long time, but that's actually fairly recent in terms of, from a scientific point of view, how we understand the structure of an atom. And the structure of that atom has allowed us then to think about chemistry even more and how they interact around the world. And the more evidence that we have, the better our understanding of chemistry becomes. So today we're looking at the history of the atom, and you can look at this little infographic here that explains some things, how it's changed over the years, and we're going to look at some of these in more detail, not all of them. So you should have this in your workbook. I'm going to read this through, and this is a timeline of people's ideas about what the atom maybe looked like and what it meant, what was an atom. So about 400 BC, so this is 400 years before Jesus, so this is 2,500 years ago, a long time ago, a Greek philosopher named Democritus first suggested that all substances consisted of tiny, indestructible particles called atoms. So we've been talking about atoms for over 2,000 years, which is crazy. And this guy, Democritus, was the first to suggest that all substances consisted of tiny indestructible particles called atoms. So that's amazing. The word atom has been around for a long time. Fast forward a long time later, 1808, John Dalton's atomic theory proposed that all matter consisted of tiny particles called atoms. Atoms could not be divided into smaller particles. Atoms of the same element were alike, and atoms combined in simple whole number ratios. So some of that seems familiar to us already. We've talked about this before, that we think, okay, atoms can't really be divided, and all the atoms of the same element are the same. So you have one proton, you have a hydrogen element. If you have 8 protons, you have an oxygen element, and those atoms will be identical, give or take a few electrons. But on the whole, 1897, the English scientist Sir Gigi Thompson explained that the atom contained negatively charged particles called electrons. His model suggested that atoms were positively charged spheres with negatively charged electrons embedded in them like a fruit plum pudding. So he basically tried to use something that was quite common to people. So in the 1800s, they obviously enjoyed plum pudding. If you think of a plum pudding, thinking of a cake that's just got a lot of, it's quite dense. And if you think of the raisins or the plums inside of it as the electrons, that's how he envisioned what an atom looked like. Not too long after that, though, Lord Rutherford proposed that the atom consisted mostly of empty space. So not this plum pudding model. And it had a dense nucleus containing positively charged protons at the centre, and the negatively charged electrons orbited the nucleus. Although Lord Rutherford's model of the atom was essentially the same as today's accepted model, its one flaw was that it proposed that the orbiting electrons would eventually lose energy and spiral in towards the nucleus. So Rutherford was fairly close with his definition of what we use today for the structure of an atom. In 1913, Niels Bohr, a scientist who had studied with Rutherford, modified the model by suggesting that the electrons orbit the nucleus at different energy levels. Only electrons with specific amounts of energy could exist at each level. His model proposed that electrons could move from one level to another by gaining or losing packets of energy. Although Bohr's model explained why electrons did not spiral towards the nucleus, it did not explain all the known properties of the atoms. So you can see here we're building on previous work and getting closer to what we believe is the correct answer. I just want to touch on the point here about the electrons moving. Remember last year we looked at stars and giving off certain chemicals giving off certain colours of light, and the way that I described that was the electrons jump up a staircase is the way I described it, and each atom has a different staircase, and when it jumps up the staircase it gives off another photon of light at specific colour. So this is what we're talking about here. I'll read that again just so that makes sense. It's all tying into what we did last term. So he said that only electrons with specific amounts of energy could exist at each level. His model proposed that electrons could move from one level to another by gaining or losing packets of energy. So that's really important when we think about chemicals giving off colours. That's what we're talking about here. And in 1932, Sir James Chadwick discovered that the nucleus contains particles called neutrons, as well as positively charged protons. Neutrons have no electrical charge and a mass about the same as a proton. So that's really important because we didn't know about neutrons until fairly recently. So less than 100 years ago, nobody knew what a neutron was. So we use that term quite a lot, and we might just assume it's been around for a long time, but that's something that's been relatively newly discovered. Okay. So let's look at these guys in more detail and see what we come up with. So Democritus, again, our Greek philosopher, he says nothing exists except atoms in empty space. Everything else is opinion. So this is amazing. Remember I talked last year about atoms being created in stars? Well, atoms are everything, and everything is made of atoms. So all we see before us is just a collection of atoms in a different arrangement to create trees, leaves, grass, clouds, humans. It's amazing. So atoms are basically the building blocks of life. And this is something that's been talked about for over 2,000 years. It's fantastic. Dalton came along with his theory, and his theory stated that all elements are made up of tiny particles called atoms. Number 2, atoms of a given element are all alike. Number 3, atoms of different elements are different. Number 4, chemical changes take place when atoms link up with one another or separate from one another. We've looked at that a little bit already. Excuse me. And number 5, atoms are not created or destroyed by chemical change. So that's ringing with Lavoisier's theory, the atomic theory of the law of conservation of mass. So this is his model, and Dalton's model was built upon later by other people. Gigi Thompson, his atomic model. Remember I said about the plum pudding? So this is kind of what he imagined it to look like. Thompson believed that electrons were like plums embedded in a positively charged pudding. Thus, it was called the plum pudding model. So we don't draw our atom diagrams like that at all. But, I mean, it's a relatively good guess given the information they had at the time. And you can understand if he's trying to figure out how does something that you can't see, how is it arranged, and he's coming up with an attempt. Then we have Rutherford. So Rutherford's atomic theory in 1911. The atom is composed of mostly empty space, so moving away from that sort of dense plum pudding model. He says small, dense, positively charged nucleus containing almost all of the atom's mass. So remember at this point they didn't know what neutrons were either, but he said the middle was positive and around it was negative. And this was called the kind of peach model, with the peach pit, or the stone. Have you ever had a peach? It's got a big stone in the middle. The stone is the nucleus, and around it is empty space, and electrons are randomly orbiting around the nucleus. So he's getting fairly close to what we use today. Niels Bohr, his atomic theory, was kind of like it had layers. Okay, so we're now getting into the sort of the electrons are in the layers, not quite electron the same way, the arrangement we have today, but he's getting close to the shells that we talk about today. So electrons do not randomly orbit the nucleus. So when we've been talking about electron shells, the inner one has 2, the next one has 8, the next one has 8. So he's getting closer to that. He said they're not random. Electrons move in specific layers or energy levels, which we now call shells. Atoms absorb or give off energy when electrons move from one level to another. So that's like the staircase I was talking about last term. It's kind of like an onion model, with electrons moving in layers of the onion and the nucleus being right in the centre again. And then we have James Chadwick, who came up with the neutron. Chadwick revised Rutherford's theory and proposed that the nucleus contains positively charged protons and neutral particles called neutrons, which is really important. One of the problems they had in this day was trying to explain the weight of the elements. The protons seemed... There's had to be something else in the nucleus giving it that weight, and they discovered the neutrons. So in the planetary model of the atom, electrons orbit the nucleus the way that planets orbit the sun in our solar system. So it's close, but again, it's not quite right because we know the electrons are in these shells. So that's a lot of information, a lot of history for you there. What I'd like you to do is pause the video here, look at the word bank on the right hand side square. All the letters, the words that we have on the right hand side will feature in the questions 1 to 7, and then we'll go over it as a group. So if you pause it here, have an attempt, and then we'll go over it together. Okay, so I'll read this out and we'll go through the answers. At the moment, the accepted model of an atom is that it consists of a small, dense nucleus made up of blank, which are uncharged particles. So what are the uncharged or no charged particles? Should be neutrons. And blank positively charged particles. So what particles are positively charged? Protons. That is surrounded by blank moving negatively charged blank. So what is negatively charged? We know they are electrons. And how are they moving? Well, they're moving really quickly or rapidly moving. So they're surrounded by rapidly moving, negatively charged electrons. Okay. In 1911, blank blank proposed the atom consisted mostly of empty space. So he has a double name. Lord Rutherford proposed the atom consisted mostly of empty space. The Greek philosopher Blank suggested all substances consisted of tiny, indestructible particles called atoms. Who was the Greek philosopher? His name was Democritus. Neutrons and blank of a nucleus are tightly bound together by the very blank blank force. Neutrons, so what do we find in the nucleus of an atom? What particles? We have neutrons and protons. They're tightly bound together by the very strong nuclear force. That's one of our fundamental forces. There is a blank force, or there is an blank forces between blank charged electrons and blank charged protons. So we talked about this last term, and I've not really explicitly said this, but there is an attractive force. Remember, positive and negatives attract. So there is an attractive force between the blank charged electrons, they're negatively charged, and the Watt charged protons, well, we know they are positively charged. Substances that are made up of only one type of atom are called blank. So substances that are made up of only one type of atom are called elements. Then question 7, blank move rapidly around the nucleus, although they follow no set path. Blank are always found in regions called blank blank. Okay, so what do we know that moves rapidly around the nucleus? We know it's electrons. They follow no set path. So electrons, again, are always found in regions called, what do we call the area they're found? Electron shells. So hopefully you got most of that. If you don't, correct your answers. And as always, we'll meet on Zoom and have a conversation about this. But I hope that makes sense to you. We've done a lot of history there. And we'll move on. It's important to understand how we've developed our understanding of the atomic theory. Okay, guys. Hot water is heavier than cold water. Thank you, Hamish. If you go and figure out why, that'd be amazing. Tell me on Zoom. See you guys.